Hello, everyone. My name is Paul James, and my colleague is Mongus Masi. We are going to present our understanding of the Introduction to Machine Learning as the diploma we studied in Allison. Uh, imagine, um, imagine teaching a computer to think, learn, and make decisions just like a human being, but faster and more precise. That is the magic of machine learning in this case, where data becomes the teacher and innovation knows no limit. So machine learning in simple terms is just the ability to give the to is the ability that okay, it is the study that gives computers the ability to learn without being programmed. So it is a computer program is said to learn from experience E given the task T and some performance measure P. So that one I've actually explained it there as the computer program gaining experience from the multiple tasks that it does repeatedly, and then it improves its performance on those tasks. Well, before machine learning came in place, there was traditional programming. Traditional programming was simple and it uses less number of rules and it was easy to program. For example, we started the problem, we write rules to that problem on how to solve that problem, then evaluate, and then we check if in the evaluation we check if actually it solves our problem. If it doesn't, then we analyze the error and we restart the problem. If it does, then we launch. Well, in the machine learning, why was there a need for machine learning in this case? Due to the complex problems that needed complex solutions for the machine learning, which involves identifying and classifying, became too robust, so it is difficult for traditional programming. Study the problem, in this case, then we trained our machine learning algorithm. Training a machine learning algorithm is like giving them the algorithm some problems, then it solves those problems. After solving them, it compares the answers is good with the already existing answers, then it makes predictions basing on those ones. So now the data that we give it is actually in terms of data sets. So when we train them, then now we evaluate the predictions made. If the predictions match the solution, then we launch. If they don't match, then we analyze and we restart it. Well, there are two types of machine learning, which is supervised and unsupervised machine learning. Supervised machine learning, this is the learning that takes place from the labeled data, and then unsupervised takes place from unlabeled data, which means that in unsupervised machine learning, we involve the algorithms. The algorithm actually involves studying the patterns and structures in the data without prior knowledge of the outcomes. Well, there are two subtypes in supervised machine learning. That is classification, which is assigning categories to data points, and regression, which is predicting continuous values. The examples of supervised learning is spam filtering in emails, and then predictive analytics in finance. In unsupervised, we have two subtypes, which is clustering, grouping similar data points together. For example, in a class whereby we have the students who like mathematics and the students who like physics. So we group such students in their own way, and then we group the students, and then we determine, we can make predictions based on those groupings. So association is finding a relationship between the variables. For example, a customer segment for targeting marketing. Well, models. A model is the representation of some phenomenon. There are basically two types, which is deterministic models and probabilistic models. In deterministic models, here the hypothesis exact relationship, so they are suitable when prediction error is negligible. In probabilistic models, these are models that make predictions based on probabilistic probability distribution rather than absolute values. Well, as we say, in the deterministic models, we make predictions based on the absolute values. Here, in the probabilistic, we make predictions based on the probability distributions. So there are probabilistic models hypothesis hypothesizes two components, that is deterministic and random error. Random error, it means that error can occur randomly within the prediction range. While deterministic, there's it the error occurs at an absolute point. So there are three types of probabilistic models, which is regression models, correlation models, and other models. Regression models are used are used to represent the relationship between one dependent variable and an unexplanatory variable. Now, there are steps when used in regression modeling. So that is hypothesize deterministic components, then specify probability distribution of random error terms, then evaluate the fitted model, then use model for prediction and estimation. Well, linear and linear regression and logistic regression, these are two regression types. So in linear regression, this is a statistic method used for predicting continuous variables based on one or more independent variables. Well, there are components, which is dependent variable, the outcome, which is the outcome you want to predict, and independent are the features used for predicting. For example, in the table, we want to find the total number of marks got by the student. We must go basing on all the marks got in all the subjects the student studied. So the coefficient is just, it represents the slope or indicating the change in the dependent variable. Then intercept is the value of the dependent variable where when all the independent variables are zero. Well, the formula of the linear regression is good from the linear function or linear formula, linear equations actually. So here, linear, let's just get from the table here the difference between the two. In linear regression, we predict continuous variables, while in this one we classify categorical outcomes. So the formulas are there, and then the outcomes are the continuous variables and probabilities on this side. Then the example here is predicting house prices, and the example this side is email spam classification. And then the assumptions made, linear relationships between variables, that is with the linear regression. And then in logistic regression, there's non-linear relationship via sigmoid function. So now, key nearest neighbors. This is this is a simple non-parametric algorithm used for both classification and regression tasks. In parametric model, you know which model exactly you will feed to the data, and in non-parametric model, it is used, the data tells you what the regression should look like. So there are 4 attributes for iris data. This include the sepal length, sepal width, and petal length, petal width, all in centimeters. So iris dataset is very classic. It is also straightforward multi-class classification dataset. Now, how does KNN works? It actually involves 3 steps. That is calculating the distance between all the training data and the test point, then finding the nearest K neighbors by sorting their pairwise distances, classifying the point based on a major vote. Here we are going to talk about 2 major key points here, which is the hyperparametrics of the algorithm based on how well it performs on the test contradicts this idea. We use the Euclidean distance if the dimensions measure similar properties, and we use the Manhattan distance if the dimensions are dissimilar. So applications of the KNN applications are text mining, agriculture, finance, and cargo competitions. Well, there are pros and cons of the KN, which is the pros is easy to explain, simple to understand, and extremely powerful. It does not require any assumptions on the data distribution. It is the first choice when there is no prior knowledge or very little knowledge. You can use it for both regression and classification. You can use it easily with multi-classes. On the other hand, the cons is the efficiency of the algorithm declines very fast as the data set grows. When you have so many data sets, our efficiency in this case declines. So it comes at a cost, making the prediction step relatively expensive. Decision trees. A decision tree is a flowchart like structure used for both classification and regression tasks. So there are components here, which is the root node, the starting point of the tree representing the entire data set. And then the example is given below. which is if you are predicting whether an email is a spam, the root node might split the data based on the presence of the word free. So internal nodes, this is a decision point within the tree where data is further split based on feature values. There's leaf node. This is the final outcome of predictions. So implementations of decision trees, there's a Gini impurity, which measures the frequency at which an element of the data set will be mislabeled when randomly labeled. The Gini impurity is calculated using a specific formula, and the formulas are given below. So Gini, there is a entropy, which is more complex since it uses logs. Gini index has only values which range from 0 to 0.5, while entropy range from 0 to 1. So one uses logs and the other one doesn't use logs. We are going to look at the pros and cons of decision trees. They are easy to interpret and visualize, and then has no assumptions about distribution because of the non-parametric nature of the algorithm. Can easily capture non-linear patterns, and then requires fewer data pre-processing from the user. For example, there is no need to normalize columns. It can be used for feature engineering, such as predicting missing values. It has no problem whether the inputs and outputs are binary, categorical, or continuous. Yes, when we go to the cons, it is sensitive to noise data, and then the small variable in data can result in different decision trees. So it is also biased with imbalanced data sets. Therefore, it is recommended to balance out the data set before creating the decision trees. It is also greedy algorithm. So greedy algorithms do not yield global optimum tree structures. All this, we got them from the course. Let me invite my colleague to present.
Hello, everyone. My name is Mercy, and I'll be taking you through ensemble learning. Ensemble learning is a supervised learning technique used in machine learning, where it improves the overall performance by combining models. Those are the weak models, also known as the base models, into one super model that is stronger and can give a more reliable prediction. The three types of ensemble learning are bagging, random forest, and boosting. Bootstrapping addresses the challenges of whether the sample population represents an entire population or the mean of the sample is a good approximation of the population. Moving on to bagging. This is a parallel tree growing with sub-samples. The idea is to create different models using different bootstrap training sets and average with their predictions to produce the final output. The steps taken using this algorithm, there is bootstrapping, where the data is divided into a number of subsets. Then base model training, where these subsets are trained independently at the same time. And then we have prediction aggregation, whereby all the trained base models, they get their predictions and put them together. Then we have out of the bag evaluation, where they take some of the samples from the base models and train them differently to see if they correlate with the base model's predictions. And if they do correlate, then you make your final predictions. Moving to random forest, this is an improvement of the bagging algorithm. It follows the steps of sampling with replacement. Then each subsample, it's chosen at random, and then we pick features of each split of this subsample, and then we build a tree on these random features with a current subsample. It has cons and cons. The cons, it's biased with dealing with categorical variables. It's slow training, and it's not suitable for linear methods that have sparse features where the data is scattered. And the greedy algorithm doesn't work well with it. Otherwise, it has a good side where it's robust outliers. It can work well with nonlinear data, and it lowers the risk of overfitting and runs efficiently on large data. Moving on to boosting, this is a technique which separates models that are trained sequentially, and they correct the mistake of the predecessors. It focuses on areas where predictions have been inaccurate and then improves them over time. And it can convert weak learners into strong learners. The disadvantage is that it can be sensitive to noisy data and outliers, and it is more computationally intensive. An example is the adaptive boosting, which is a type of boosting technique that assigns weight to instances to iteratively improve classification accuracy. It's robust against overfitting, and it's simple to implement with high degree accuracy. Otherwise, it requires careful tuning of hyperparameters to achieve optimal performance. Then moving on to the support vector machine. This is a supervised machine learning algorithm used for classification and regression. How it works, it finds the maximum separating hyperplane between the different classes in the target feature. And the target plane, they can be hard margin or soft margin. Hard margin, which is known as maximum margin hyperline, where the data is assumed to be perfectly separated. And for soft margin, the data is not perfectly separated. Then moving on to the types of the support vector machine, we have linear, nonlinear, and support vector regression. When you talk about linear and non-linear, that's linearity, where in linear, it uses linear decision boundary to separate data points of different classes. Then in non-linear, it classifies data when it can't be separated by a straight line. And here it uses kernel functions. In the support vector regression, it predicts continuous values by ensuring predictions stay within a margin of tolerance around the actual data points. Moving on to the next, the cons and pros. These are high dimension performance algorithms, and its nonlinear capabilities can work with nonlinear data. It's resistant to outliers, it can work with binary and multi-class supportive, and it's memory efficient. Otherwise, it has the bad side of it being slow, and it's difficult to tune the parameters, and it's noise sensitive, it's limited interpretability, and it's very sensitive to feature scaling. Then moving to the principal component analysis. This is an unsupervised learning algorithm technique used to examine interrelations among a set of variables. It's also known as a general factor analysis, where the regression determines a line of best fit. Here, the goal is to reduce the dimensionality of data. You have to reduce the distance between the data while preserving the most patterns between the variables. Then we have how it works. That is, it identifies the principal components. It orders components by the amount of variance they explain. Then it discards the components with minimal variance. Otherwise, it has drawbacks. That is, it's very sensitive to scaling and outliers. It assumes linear correlation between variables, yet it's not usually the case. And visualization is usually difficult with the principal component analysis. So we have application of the principal component analysis. Pre-processing. The pre-processing, here we have the classification and clustering. Then the facial recognition, where it can recognize someone. Then we have the data visualization, where it is easy to visualize data. Then image compression, where it keeps on reducing the size of the image while maintaining the main features that are needed to identify that maybe this is a hippopotamus, this is a human being, this is a cat. Yes, thank you for listening.